So the first half of the chapter will introduce the Gauss law for magnetic field, and also it will do some modification to the Ampere's law. So in this textbook, it is called the Ampere-Maxwell law. So it adds another term on the right hand side of the Ampere's law. So and up to this moment, then we have already learned 4 laws: two Gauss law, and 1 Ampere-Maxwell's law, and also Faraday's law. So these 4 laws are called the Maxwell Equations. And in the second half of the chapter, it talks about some hardcore physics, which is about the magnetism. You can feel like it's just a story. It's hard to be tested on the exam. So, and it is some sort of hardcore stuff. Even for me, I don't think I know it very well. So I just let you know a bit about some sort of the hardcore physics. Okay, so here we talk about the laws for the Gauss law for magnetic field. So in chapter 23, we have learned the Gauss law for the electric field, which is like E dot dA epsilon naught equals Q enclosed, if you still remember. So this one, we have Q enclosed. Of course, we will define a Gaussian surface, and then we will apply the Gauss law on it. So on the left side, we have the surface integral E dot dA, and then multiplied by the epsilon naught, the permittivity. So this integration would be quite difficult to calculate, but it always equal to the charge enclosed. So for the magnetic field, on the left side, we have also the B dot dA. But on the right side, we don't have magnetic monopole. As I have discussed it in chapter 29 or 30. I don't really, maybe chapter 29 or chapter 28. We've already mentioned that there isn't any magnetic monopole, so we don't really have some sort of positive magnetic or negative magnetic. It always appears in a pair. It doesn't like the charge. You can have positive charge or negative charge independently. So in this case, when you draw a Gaussian surface, the enclosed magnetic dipole will always be will be something like you have positive and negative, and they always cancel each other. So on the right hand side, you only have 0. At that time I mentioned that if you have an equation with epsilon naught E, and then you can always change it to epsilon naught to 1 over mu naught, and then B dot dA equals 0, because we don't have charge. But actually, since the right hand side is 0, so we can just multiply mu naught on both sides. So it turns out to be like this. So it doesn't rewrite the term 1 over mu naught here. Or you can also derive epsilon naught on both sides, so that the left hand side is the surface integral, the right hand side is Q enclosed over E naught. So for the magnetic field, we don't have magnetic monopole, so we have only 0 on the right hand side. So it's just like if we have a long magnet bar, if we cut it into 3 pieces, so it will like ns, ns, ns. So it will still become magnetic monopole individually. Okay, so next we talk about the induced magnetic field. So in chapter 29, when we talk about the Ampere's law, it is like B dot ds equals mu naught I enclosed, if you still remember. Okay, so at that time it is only for static current. If the current don't really change, so we have this line integral equals to the current enclosed by the Ampere's loop. So in this case we have another expression. This is called the changing electric flux. So the induced magnetic field B, this is called the Maxwell's law. So on the left side we still have this line integral, but on the right side we have these terms mu naught epsilon naught d phi e dt. Yeah, and compare with chapter 30, the Faraday's law, we have E dot ds equals minus d phi b dt. Yeah, if you still remember. Yeah, so for the Faraday's law, it is like if we have changing magnetic flux, there will be some induced electromotive force. Yeah, so in this case, if we have a changing magnetic flux, then there will be magnetic field generated. So related to the magnetic field induced along a closed loop to the changing electric flux phi e through the loop. Yeah. So suppose we have a capacitor. We have some current charging this capacitor. In this case, as much as we have a dq dt equals I. So as much as I is a positive, which means that the Q is increasing. And also we have a Q equals CV, which means that as long as a Q is increasing, the voltage difference or the potential difference between the parallel plate are also changing. And in that case, you also have E equals VD. D is the distance between the parallel plate. So as much as V is changing, so E is also changing, which means that the E field between the parallel plate are changing, which means that the electric flux is also changing. So as much as the E field, the electric flux are changing, so there will be some magnetic field induced here. So as an example, sort of induction, we consider the charging of the parallel plate capacitor using the circular plate. So we assume the parallel plate are circular. And now we define the Ampere's loop here. So now you assume that this is E field going into the page in this graph. So you just change a 90 degree, shift a 90 degree. So you see it from this side, and then it becomes this figure. So now as much as E is increasing into the page, so you can use the right hand rule, which means that your forefingers follow this direction, and then your thumb will be pointing into the page. So, and this means that your thumb follows the direction of a d phi e dt. As much as E is pointing into the page and E is increasing, so d phi de is into the page. So your forefinger should be clockwise, which means that the generated magnetic field should be somehow like clockwise, And yeah, so for each point, for example, for this point, the magnetic field is pointing downward. For this point, the magnetic field is pointing to the left side. For this point, the magnetic field is pointing upward. Yeah, so the electric field magnitude between the plate must also be increasing at the steady rate. So for simplicity, it just assume the E field is changing in a constant rate or steady rate, which means that d phi e dt is just a positive constant. It's just a positive constant. Okay, so a changing electric field in the let me see. Yeah, so the electric field is directly into the page. So consider a circular loop through point 1. So this point, a loop that is concentric with the capacitance plate. So this impedance loop, and this circular plate shares the same center. So a loop that is concentric. Yeah. So so because the electric field through the loop is changing the electric flux through this loop, so we consider the electric flux through this loop must also be changing. According to the above equation, this changing electric flux induces a magnetic field around the loop. Yeah, so so this is called the Maxwell's law, and we can also compare it with the Faraday's law. So we have a changing E field generate magnetic field, and also we have a changing B field generate electric field. So they are similar but different in two ways. So mu naught and epsilon appear for matching SI unit. So for Faraday's law, we don't have this constant. But for mu naught, epsilon naught, so the terms are there so that the SI unit will match. And actually, in the next chapter, you'll know that this constant has some physical meaning, as much as C is 1 over square root of mu naught epsilon naught. So this C is called the speed of light in the vacuum. So this is speed of light. So yeah, so this value should be 2 So this is speed of light. This is the speed of light up to 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits. Or sometimes we usually use 3 times 10 to the 8th power meter per second, or in modern physics we will sometimes use 2.998 times 10 to the 8th meter per second. Yeah, in another semester I'll teach the special relativity. So in special relativity, we will use 2.998 times 10 to the 8 rather than 3 times 10 to the 8. Yeah, so so this constant has the SI unit of second square over meter square, because this is meter per second. So if we just take the inverse and then take the square, so this term has second square per meter square. And then the next point is the negative sign for the Faraday's law means the induced electric field is So this is the main difference between these two laws. So for the upper graph, as much as we have E field pointing into the page and it is increasing, then the B field should be somehow like clockwise. For the positive sign, of 32.3. But here, suppose we have barely with the same graph, but here we have the magnetic field pointing into the page, and we assume the magnetic field is increasing. And in that case, as much as we have the negative sign, so the induced E field should be somehow like counterclockwise. And this is due to the positive sign of 30/20. Yeah. Still, you use the right hand rule, you use your thumb pointing into the page and your fingers are clockwise. But for this one, we only have positive sign, so the generator B field also clockwise. But for this one, our forefinger are pointing clockwise, but here we have a negative sign, so the generator E field are counterclockwise. Okay. And so just now I already mentioned that in chapter 29 we already mentioned this line integral equals mu naught I enclosed. Suppose the I doesn't really change with respect to time. So we have the Ampere's law, and now we also have the Maxwell's law. This is for the case that the electric field is changing with respect to time. So actually, for the Ampere's law, or in this textbook, it explicitly call it Ampere's Maxwell's law. So we just add the right hand side together. So overall, we have B dot ds equals mu naught I enclosed plus mu naught epsilon naught d phi e dt. So we just include both together, so that in this textbook it's called Ampere Maxwell's law. So when we use this one, sometimes we only have a constant current, so that this term will be zero, because for constant current we don't have a changing E field, so this term will be zero. This term vanish, and then it is changed to the Ampere's law. If we don't have a constant current, you only have the changing E field, then this term will vanish, and then this law will change to the Maxwell's law. So we can directly use this one, and it depends on the situation, and then sometimes one of the term will just vanish. Okay, so when there is a current but no changing electric flux, such as Y carrying a constant current, the first term on the right hand side of the equation is zero. And so the equation reduced to Ampere's law. Also, when there is changing electric flux but no current, such as the inside-outside gap of charging capacitor, the second term of the right hand side of the equation is zero. So the equation reduced to Maxwell's law of induction. So I just mentioned it. Yeah, so let's see an example. Okay, here, so we still have the same figure. We have a circular capacitor, and so we have the changing E field. So a parallel plate capacitor with the circular plate of a radius r being charged So derive the expression of the magnetic field at radius r for the case that r is smaller or equal to capital R. So this is small r, this is capital R. The capital R is the radius of the circular plate. The small r is the radius of the ambient loop. Okay, so now we can apply the Maxwell's law, or before I just call the whole one the Ampere's law. Okay, so we can now apply the Maxwell's law. So we have the line integral B dot ds equals mu naught epsilon naught d phi e dt. So, and due to the symmetric, we can just simplify this part as B ds equals mu naught epsilon naught, and now we assume that the E is changing. So it is nothing but E times A, because originally the phi E for the original definition should be like E dot dA, something like this. And yeah, this is not a closed surface because we only consider this surface enclosed by the ambient loop. So we only consider this surface when we do the surface integral for the and as much as E is uniform and pointing into the page parallel to dA, so it is nothing but EA. So next step is D is nothing but B times 2 pi small r. So we assume it is uniform, so it is like B times the circumference of the circle, so 2 pi r. And then we will have mu naught epsilon naught, and then A should be a constant because it doesn't move physically, so A can be factored out. So we have a dE dt because E should be changing with respect to time. So this is nothing but mu naught epsilon naught pi r squared, the area of a circle, dE dt. So finally, B should be mu naught epsilon naught pi and pi can be cancelled, and then r and r squared can be partly cancelled. So we have r over 2 times dE dt. So this is the expression for the magnetic field inside the capacitor, inside the parallel plate. So next, evaluate the field magnitude B for R equals capital R over 5. And then dE dt equals 1.5 times 10 to the 12 voltage per meter second. So this is nothing but B should be mu naught epsilon naught R over 2 dE dt, and then we just substitute the values. So mu naught is 4 pi times 10 to minus 7, and then epsilon naught is 8.55 times 10 to minus 12 times R is 11 millimeter, 11 times 10 to minus 3rd power, all over 2 times dE dt is 1.5 times 10 to the 12th power. So this is 9.18 times 10 to the minus 8 Tesla. Okay, so we just substitute the number into the expression we just derived. Okay, so the next one is derive an expression for the magnetic field and the radius r is larger than capital R. So we should include a amperance loop like this. So now we have this out rather than this one. We don't have that one. Yeah. So still we have B dot ds equals mu naught epsilon naught d phi e dt d phi e dt. Okay, so so on the left hand side we still have b times 2 pi small r. It should be the same. But for the right hand side, we still have mu naught epsilon naught a dE dt. Yeah, up to this part, up to this step, it should be the same as the previous case. But here, the A is different from the previous one. Yeah, because when we consider the electric flux, there's only electric flux inside the capacitor plate. There is no electric field outside the capacitor plate. At least we assume this to be like, yeah, we assume there are no fringe effect. So we assume there are no electric field outside. In this case, this A should be mu naught epsilon naught pi capital R squared rather than small r squared. So dE dt. So in this case, B should be mu naught epsilon naught pi and pi cancel. We have R squared over R squared. R squared over 2 small r times dE dt. So actually I suppose we have to do some similar calculation for the original Ampere's law. So you have similar expression like this. The only difference is that now we have this one, but at that time we have I enclosed, so that you need to calculate the I enclosed. What I enclosed is for different cases, assuming the current is uniform over the wire. Okay, so yeah, okay, so here we introduce a concept called the displacement current. Displacement current. In Chinese, it is called yeah. So displacement current. So if you compare the two terms on the right hand side of the equation, Ampere's Maxwell's law, you'll see that the product, this term must have the dimension of the current. In fact, that product has been treated as being a fictitious current called the displacement current, ID, which means that suppose we have this equation, and yes, suppose that it should satisfy all the SI units. So we have mu naught times I enclosed, and also you can see something like, this is mu naught. So this term should be something like a current. Should be something like a current. Yeah, and in that case, we call this term the displacement current. The displacement current. So we call this one ID. We call this one ID. So that in this case, if we just substitute this back to the Ampere-Maxwell's law, the right side will become mu naught I enclosed plus ID enclosed. ID means the displacement current. So yeah. And actually, you can just regard the displacement current is the current going through the capacitor, So it is like ID equals epsilon naught dE dt, d phi E dt. Okay, so just now we assume that it is a parallel plate, and then the E field is uniform and parallel to the area vector. So it is like epsilon naught A dE dt. So we assume uniform and E field. Okay, so next we have E naught A over D times D, E times D dt. So if you still remember, E times D is V, so we have epsilon naught A over D, and then times D V dt. So this is the parallel plate capacitance. So we have, this is C dV dt. So this is the C equals epsilon. So this is a parallel plate capacitor. Parallel plate capacitor. So we have this C, and then dV dt is here. V equals ED for uniform E field again. So you can see that this displacement current is actually the current going through the capacitor. Yeah, so finding the induced magnetic field, we find the direction of the magnetic field by real I using the right-hand rule. So just now I already mentioned that you can use the right-hand rule to determine the direction of the generated B field or generated E field according to the Ampere's law, Ampere-Maxwell's law, and also the Faraday's law. So we can apply the same rule finding the direction in the induced magnetic field produced by the fictitious displacement current, which means that your thumb will follow the direction of the current. Then, as done by previously, the magnitude of the magnetic field at the point inside the capacitor at radius from center is like this. Actually, we just derive it. We just derive it like here. Derive it like here. So you can let me see. Yeah, so so this is for another case. This case is different from that one. So for this case, it is like if we have a current. If you still remember this one, this one is like if we have a current, constant current, then the generated B field should be like B equals mu naught I over 2 pi, this is R. Actually, you can use the Biot-Savart law to really derive this one. If you don't remember, you can check back the chapter 29. So now if we have the displacement current, something like we have something like this, then the generated B field, is something like B equals mu naught ID over 2 pi R, which is this expression. So if we consider, this is a so this is a cross section. This is the cross section area, and suppose, and actually I don't think, yeah, something like this. And you assume there are ID going through this cross section, and if you consider the magnetic field here, then this B is something like mu naught I ID times R over R squared. Yeah, you can still follow the previous steps. It is like the whole one has ID. So for this cross section, it is like pi R squared over ID is pi small r squared over ID enclosed. So when you really imply, if you really apply the Maxwell's law, so it will be like B times 2 pi R equals mu naught I enclosed. I enclosed is actually ID times let me see, let me write one more step. So this is ID enclosed. So ID enclosed, you can just have ID enclosed equals ID, and then times pi r squared over pi capital R squared. So it is nothing but ID times small r squared over R squared. And then you can just substitute it here. We have mu naught ID times small r squared over capital R squared. So if we just simplify it, we have a B equals mu naught ID times R over 2 pi capital R squared. Yeah, so we can use the Maxwell's law to really derive similar expression. The only difference between this one and the one we derive in chapter 29 is that for that one it is constant current. For now it is a displacement current. So the expression should be the same. Yeah, you just change I into ID. So you have actually the steps to derive it are actually the same. Okay, so here let's take a look at this sample problem. So for the circular plate capacitor is being charged with a current I. So we have current I between the plate. What is the magnitude of B dot ds in terms of mu naught and I at radius R? So we have B, let me So we have B dot ds equals mu naught ID enclosed actually I just already derived it. So actually this is nothing but ID enclosed over ID equals pi small r square over pi capital R square. So here we can just substitute back here. So we have mu naught ID enclosed. We have ID times small r square over capital R square, and then small r square. Small r is capital R over 5. So we have capital R over 5 quantity square over R square. So we have mu naught I over 25. Yeah. So actually this is not different from the previous one. This is different from the previous one. So you need to be careful that this is the parallel plate, and then we consider the magnetic. Yeah, still we consider magnetic field here. Yeah, actually it's to be the same. Yeah. Okay, so for part B, in terms of the maximum induced magnetic field, what is the magnitude of the magnetic field induced at small r inside the capacitor? So we know that B of R should be mu naught ID times R over 2 pi capital R square. So this is proportional to R. So this is a constant multiplied by R, which means it is proportional to R. And of course, so B of R over B max should be B of R is capital R over 5, and then the maximum K should be B of R, because this one satisfies when R is smaller or equal to capital R. And if small r is larger than capital R, then B start to decrease. So the maximum point should be at this one, at this point. And so this one should be nothing but 1 over 5. Because we just plug in this one here, plug in this one here, and plug in this one here. So we just have 1/5, which means that the B of R should be 1/5 B max. So up till now we have studied all the laws in the Maxwell equations. So the 4 fundamental equation of the electromagnetism is called the Maxwell equation. Yeah. So and of course in the electromagnetism there are some other laws which are also important, but at that time Maxwell just summarize that these 4 equations are the most useful ones. And actually nowadays, if we are using some sort of electromagnetism simulation tool, then actually it is try to solving the Maxwell equation and actually solving the differential form for the Maxwell equation. Actually, this is the integration form, and I will let you know the differential form next week, I suppose. Yeah. So these four equations explain the diverse range of phenomena. They are the basis of the functioning of such electromagnetic device. As electric motor, the television transmitter, receiver, telephone scanner. So nowadays we will use it every moment. And of course, we have two Gauss law, one for electricity, one for magnetism. So you can see these two terms on the left-hand side. The only difference is E and B. And also we have Faraday's law and Ampere-Maxwell's law. So the left side is nothing. It's actually the same. The only difference are also E and B. So this is surface integral. This is line integral. And for the first two, the Gauss law, we have Q enclosed over epsilon naught. And for the magnetism, we don't have a magnetic dipole, magnetic monopole, so we have only 0 on the right side. And for the third and fourth one, we have a changing E field. We have changing magnetic field. It generates E field. The changing magnetic field will generate electric field. And also here, if we have changing electric field, it will generate magnetic field. Also, the static current will also generate the magnetic field. So these are called the Maxwell equation. And let's have a 10 minutes break.